Welcome back to Maths with Mrs. J. In our previous video, we talked about de Moivre's theorem and we proved it by induction. Now we're actually going to see how useful that theorem is. Just reminding you that de Moivre's theorem says that if you have a complex number in polar form, so r cis theta, and you want to raise that complex number to the power n, then you have your r to the n, which is obvious because that's just an index law, but then that cis of theta raised to the n is just cis of n theta, which is kind of cool. Let's have a look at some examples. Here we've got an example here where we've got cis of pi on 3, we want to raise that to the power 9. What de Moivre is saying is that all we have to do is multiply that argument. And the great thing is that we get cancelling happening here, so we get cis of 3 pi. Now, just thinking back for a minute to our diagram, where is 3 pi? You've gone around by 2 pi and you've gone around by pi more. So 3 pi is here, isn't it? So remember that cis means cos plus I sine of that angle. Well, what's cos of 3 pi? Cos of 3 pi is -1. What's sine of 3 pi? What's the y value there? It's nothing. So this whole thing is just equal to -1, which is kind of cool. All right, let's look at our next example. Let's leave the numerator as is for now. In our denominator, the rule says that we're going to multiply that argument. Okay. Then we are going to, using our rules about dividing complex numbers in polar form, we're going to subtract those angles. You could, by the way, 7 pi on 3 is really 6 pi on 3 plus another pi on 3. Let's maybe do that, just to make sure that we're working with our easiest possible angles. So this is really just cis of pi on 3. So when we do this using our subtraction, put them all over 12, and what do we get? 21 pi minus 4 pi all over 12, which is cis of 17 pi on 12. Okay, now this last one might not immediately look like something where you'd use de Moivre's theorem, but in fact, it's the perfect chance to use de Moivre's theorem. If you were to have to expand out numerator and denominator, it would be a little bit of a pain to do and collect your terms and everything, and then you'd have to multiply by your what am I trying to say? The conjugate surd, the conjugate complex number over the conjugate complex number. That would be a bit of a pain. However, if we could convert each of these into their polar form and go from there, we might well find it to be a lot easier. Just having a quick look for a minute at 1 plus I. So 1 plus I is here. So it's in the first quadrant. What's r going to be? R is going to be square root of 1 squared plus 1 squared, which is √2. Tan of theta is going to be 1. And in our first quadrant, we know that theta will be pi on 4. So we can convert the numerator fairly easily into √2 cis of pi on 4. And all of that is cubed. The complex number in the brackets in your denominator, let's think about that one for a minute. So we've got, what have we got? So we've got 1 minus root 3i. So we're down here, so we're in our 4th quadrant. So r again will be square root of 1 squared plus 3 squared, so it's square root of 4, which is 2. Tan of theta will be your negative root 3 on 1, and we're in our 4th quadrant. Remember what I said, you've got to be a little bit careful about inverse tan. You wouldn't want to do it on your calculator here anyway, because you wouldn't get the exact value. But we're going to either have a negative angle or we're going to have 2 pi minus that angle. The relative angle in the first quadrant is pi on 3, isn't it? So I'd put this one as negative pi on 3. So I'd do, so this is 2 cis negative pi on 3, all raised to the 5. Now de Moivre's theorem comes in. So root 2 cubed is 2 root 2. We bring this in as a multiplier, so 3 pi on 4. And in our denominator, we're going to get 2 to the 5. Let me just get rid of that. Try again. So we're going to have 2 to the 5, cis of, and we're going to multiply again, so negative 5 pi on 3. Now, what are we going to get? Well, negative 5 pi on 3 is in fact, if we think about it, is the same as pi on 3. Does everybody get that? Because it's 6 pi on 3 is 2 pi. So if you've gone back by negative 5 pi on 3, you're actually at pi on 3. And one of these 2's will cancel. So we've got root 2 cis of 3 pi on 4 over 16 cis of pi on 3. Now we're just going to do our subtraction of these angles. 3 pi on 4 minus pi on 3 is 9 pi on 12 minus 4 pi on 12, which is 5 pi on 12. And there you have it.